I have an integral that I would like to evaluate here, and there are a couple of things that make it challenging. Number one, I'm integrating to infinity. So this is an improper integral. I'm going to need to use a limit to evaluate this thing. Maybe it will give me a finite answer, maybe it will diverge. And then the other thing is, I don't know how to find the antiderivative of this. At least nothing comes to mind that I could do simply. The issue is the cosine x over x. Not exactly sure how to do that. If it was just 2 over x, I could handle that no problem. So what I'm going to do is think about what this function acts like. I want to find something that's more simple that I can actually integrate that behaves similar to this. So when I look at this thing, the 2 and the x aren't giving me a problem. It's the cosine that's giving me a problem. And I know that when you think about the graph of cosine, it bounces between -1 and 1 in the y value. So if I do 2 plus cosine, since cosine is between -1 and 1, when you add 2, the smallest you can get is a +1. So basically I'm just adding 2 to everything here. The smallest I can get is a +1. And then cosine plus 2 is the numerator. So that numerator is always between 1 and 3. And I can actually integrate 1 over x or 3 over x. And I think I remember from a problem that I've worked on before, I think when I integrated from 0 to infinity of 1 over x, that gave me an infinite area so that this thing diverged. If that's true, and this numerator is at least as big as 1 the whole way, and sometimes it goes all the way up to 3, then I would expect that it would still diverge. Because if this has infinite area when I just go from, when I look at 1 over x, and making it bigger, making it have more area, it should still diverge. That's a theorem that I'll write down later. For now, I want to go ahead and integrate 1 over x. And I also want to point out, this tells me that if I look at 1 over x, that's less than or equal to this thing over the interval. Oh, you know what? I want to. There's another problem. I'm dividing by 0 here. Before I started, I had e to the x down here, and I changed it. So I'm gonna start my integral at 1 instead of 0. From 1 to infinity, this function is less than or equal to this one. And this is less than or equal, it's positive, it's greater than or equal to 0. I guess I could say it's strictly greater than 0. So because of that, if this diverges, then this definitely diverges. So let's go from 1 to infinity, 1 over x. So remember, what I have to do is integrate from 1 to some value, some variable value, I'll just call it t, and then let that t slide out to the right, take the limit as t goes to infinity. I know the antiderivative here. Natural log of absolute value of x. My bounds are positive, so I don't need the absolute value. Plug in the bounds. And then this natural log of 1 is constant, so I don't need to worry about that. And it also happens to be 0, so I could ignore it because of that as well. But in the limit, this is the only part that changes. So I need to figure out, as t goes to infinity, what happens to natural log of t. And if you remember the graph of natural log, it looks like this. It's the inverse of y equals e to the x, which looks like this. So if you flip over the line y equals x, from y equals e to the x, you get y equals natural log of x. And so as I go out to the right here, I want to know, is this going to continue to go up, or is it cutting off at a horizontal asymptote? If I go up here forever, it keeps on going to the right forever. So because y equals e to the x keeps going to the right forever, this natural log of x keeps going up forever. So this limit is infinite. Goes to infinity. So this integral diverges. And again, because our function is greater than or equal to this positive function 1 over x on this entire interval, this one has more area at every finite step of the way. So this also has to diverge. So what I would say is, by the comparison theorem, this integral also diverges. And I want to write out a formal statement for the comparison theorem. There are two different versions of it. There's this version that we used, and then there's another version where you can say that something converges. So there are multiple contexts where you could look at a comparison theorem. This is the comparison theorem for improper integrals. The setup is you have a couple of functions that you know are both positive. And you know that one is bigger than or equal to the other one on some interval. I'm going to start it at a finite number and go out to infinity. So maybe I should say suppose this period, then there's a couple of things. If I know that the integral of f of x is infinite on a to infinity, then the integral of g must also be infinite. That's what we just used, so I'll write that down. The integral from a to infinity f of x, as a loose shorthand, I'm going to say equals infinity. I really mean if this thing diverges, then the integral of this one must also diverge. I'm going to say equals infinity instead of diverges. And then second, if we integrated the bigger one and we found that it converges, so the area is finite, then the area of the smaller one must also be finite. So the integral from a to infinity of the big one is finite. That has to imply that the integral of the smaller one is also finite. That's the comparison theorem. We use this top one. This bottom one is good to use also.